Good day, my name is Agali Belinda Chizoba. I'm taking you on the subject chemistry and on the topic electropotential and electrochemical cells. At the end of this lesson, you're supposed to define electropotential, define standard electropotential, describe the hydrogen electrode, determine the electropotential of a metal, calculate the E.M.F of a cell, describe electrochemical cell, and list the types of electrochemical cells. If a metal plate is placed in a solution containing its ions, for example, a solution of one of its salts, some of the atoms from the metal plate will ionize and go into solution as positively charged ions, leaving behind their valence electrons on the surface of the plate. At the same time, some of the metallic ions in the solution will take up the electrons from the plate and deposit themselves as neutral atoms on the plate, leaving behind an excess of anions in the salt solution. If reaction 1 is the metal going as metal ions, the metal plate or electrode becomes negatively charged with respect to the solution of the electrolyte. But if reaction 2 is favored, the electrode becomes positively charged with respect to the electrolyte. A potential difference known as the electropotential for the metal ions and metal system is set up between the metallic electrode and the electrolyte solution. That is the difference between reaction 1 and reaction 2. The electropotential is a measure of a tendency of a metal in a solution of its salt to form ions. The value of the electropotential of a particular metal depends on 1. The concentration of the metal solution, 2. The temperature of which the measurement was taken, and 3. The atmospheric pressure. In order to compare electropotential for different metals, a 1 molar solution of the metal ions and a temperature of 298 Kelvin is specified as standard electrode potential. The standard electropotential of a metal ion and metal system is the potential difference set up between the metal and a 1 molar solution of its ions at 298 Kelvin. It is not possible to measure the absolute value of the electropotential directly. Instead, it must be measured against some reference standard. The reference standard electropotential is the electropotential of the hydrogen ions or hydrogen gas system and is taken to be 0 volts. The hydrogen electrode is made by passing hydrogen gas at 1 atmospheric pressure over a platinum wire coated with finely divided platinum black and immersed in 1 molar HCl. Bubbles of hydrogen gas are seen at the surface of the platinum. The electropotential of a metal is determined by connecting the half cell of the metal, that is the metal dipped into a solution of its ions, and connected to the hydrogen electrode, which is the standard electrode, through a salt bridge, which is connected between the half cell and the hydrogen electrode. The salt bridge serves as a conducting link between the two solutions. The voltmeter records the electropotential of the metal in volts. For example, the electropotential of zinc metal can be determined by the zinc metal in a zinc salt solution, for example, zinc tetrahydrosulfate 6 solution, connected to the hydrogen electrode through a voltmeter. Salt bridge is connected between them, that is the zinc metal system and the hydrogen metal system, and the voltmeter records the electropotential. Since zinc is higher than hydrogen in the activity series, electrons will flow from the zinc electrode to the hydrogen electrode. Therefore, the zinc electrode undergoes oxidation, while the hydrogen electrode undergoes reduction. You can see the reaction here. Zinc is undergoing oxidation to form zinc 2+, while hydrogen is undergoing reduction to form hydrogen gas. When the two half cells are connected together through a voltmeter by means of salt bridge, there is a potential difference between the two half cells. Thus, the E.M.F of the cell can be calculated mathematically. That is, E.M.F of the cell is equal to E.M.F of the cell on the right hand minus E.M.F of the cell on the left. The E.M.F of the cell on the right hand is the one that is undergoing reduction, while on the one on the left is the one undergoing oxidation. For example, calculate the E.M.F of the following cells at 298 Kelvin between iron and tin, zinc and silver, nickel and copper, silver and fluorine, given that the E.M.F of the metals and elements are, for iron 2 ion, is minus 0.44 volts, tin 0.14 volts, zinc 0.76 volts, silver plus 0.80 volts, nickel minus 0.25 volts, copper plus 0.34 volts, and fluorine gas plus 2.87 volts. Solution: for this system, we are going to use E.M.F equal to E.M.F reducing cell minus E.M.F oxidizing cell. Since the E.M.F of iron and iron 2 ion is plus 0.14 and that of tin is minus 0.44, if you subtract this from this, you get plus 0.30 volts. For the zinc ion and silver ion system, we are also going to use the same formula, E reducing minus E oxidizing. Silver is reducing, we are going to use the E.M.F here, and this one is oxidizing, we are going to use the E.M.F here. That is plus 0.80 minus 0.76 to give you plus 1.56 volts. Then for C, we use E right minus E left. That is plus 0.34 minus 0.25 to give us plus 0.59 volts. And lastly, E reducing minus E oxidizing plus 2.87 minus plus 0.80 to give us plus 2.07 volts. Electrochemical cell. When a stripe of metal such as zinc or copper is dipped into a solution of its salts, an electrical potential difference is set up between the metal and its ions at equilibrium. This is represented as M solid going to form Mn plus. The slanting line represents the boundary or interface between the solid and the liquid. Under this condition, the setup constitutes a half cell. When two different half cells are separated by a porous partition, a salt bridge, that allows the diffusion of ions, electron transfer occurs externally through the connecting wire, that is a conductor, between the two electrodes, as indicated by the glowing of a bulb or a deflection in the voltmeter. Such setup is called a galvanic, voltaic, or electrochemical cell. The flow of electrons through the conductor constitutes an electric current. This is a diagram of an electrochemical cell. Here we can see the two metals dipped inside the salt solution, and then current flow going from the anode through the solution to the cathode, while electron flows from the cathode through the solution to the anode. An electrochemical cell can be described as a device that uses a spontaneous chemical reaction in an aqueous solution to generate electric current. That is, it converts chemical energy into electrical energy. Once chemical reaction occurs, that is oxidation and reduction reaction, we will have current flow. We have two types of electrochemical cell, the primary cell and the secondary cell. The primary cell is used to generate small currents of electricity for everyday purpose. Examples of primary cells include Daniell cell. The Daniell cell consists of a copper vessel filled with a saturated solution of a copper 2 tetrahydrosulfate 6 and a porous pot filled with a zinc tetrahydrosulfate 6 solution. Immersed in the zinc sulfate solution is a zinc rod. The two electrolytes are separated by the salt bridge. The salt bridge allows for transfer of common ions but does not allow the mixing of the two electrolytes. It is represented as a double slanted line in the cell diagram. The salt bridge could be made by soaking a filter paper in sodium chloride, potassium chloride, or ammonium triisonitrate 5 solution. The cell diagram for a Daniell cell can be represented as this. This is the zinc rod that is immersed in a zinc salt solution, while this is the copper tetrahydrosulfate 6 salt that is going to be deposited as copper solid. The zinc rod will dissolve by loss of electrons to form zinc ions, that is oxidation reaction, while the copper 2 ions in the solution accept electrons from the electrode to deposit shiny brown copper metal, which is reduction. Hence, in the Daniell cell, a redox reaction is used to produce electric current, no external battery. The dry cell, or dry Leclerc cell. The popular battery is being sold under trade names such as Berek and Tigerhead, which are used in torches and radios, are examples of dry cells or Leclanche cells. In a dry cell, the casing is made of a zinc metal container as the anode and a graphite rod surrounded by manganese 4 oxide as the cathode. The electrolyte is a paste of ammonium chloride, and the cell diagram can be represented by zinc going to form zinc ion and ammonium ion being deposited as ammonia gas plus hydrogen gas. The zinc atoms lose 2 electrons each to dissolve in the electrolyte as the zinc ions, while the ammonium ions accept the electrons to become reduced to ammonia and hydrogen gas. The hydrogen gas is removed by the manganese 4 oxide. The secondary cells are cells which can be recharged. They are recharged by passing a direct current through them. An example of a secondary cell is the lead accumulator used in motor cars. The cathode and the anode are lead 4 oxide and metallic lead. Lead accumulator produces electricity by discharging. During the process of discharging, lead atoms release 2 electrons each to become oxidized to lead 2 ions, which then combine with the tetrahydrosulfate 6 ions in the electrolyte to become deposited on the anode as lead sulfate. The electrons released, which is this, pass through an external circuit as an electric current to be used for starting the engine of a vehicle or lighting the car lamps before arriving at the cathode. When the electrons arrive at the cathode, the lead 4 oxide and the hydrogen ions from the electrolyte undergo reduction to produce lead 2 ions and the water. The lead 2 ions then combine with the tetrahydrosulfate 6 ions from the electrolyte to become deposited at the cathode as lead 2 tetrahydrosulfate 6 ions. During the discharging process, the density of the acid decreases due to the absorption of hydrogen and tetrahydrosulfate 6 ions from the electrolyte. When both electrodes are completely covered with lead sulfate, the lead accumulator stops discharging current, hence it will have to be recharged. During the process of recharging, the electrodes in the cell are reversed because it is electrolyzed. The electrode, which is the anode in the charged cell, becomes the cathode, while the cathode becomes the anode. After this lesson, you can use it to evaluate yourself. What is electrode potential? What element is used as a reference electrode? Calculate the standard electrode potentials of the following cells, given that this is this. List 2 examples of primary electrochemical cell, and what is the electrolyte used in a secondary electrochemical cell. At the end of this lesson, we have discovered that we have a chemical reaction that helps to generate currents for small torches, radios, and also our cars, which we use to light the bulbs. You can now calculate the E.M.F of the cell using the hydrogen electrode as a standard electrode. Thank you.